At this point, I want to comment, give some comments on the methodology we used. Actually, I will wrap up again what we did actually. In the previous lecture, we have this very simple differential equation, d2u of x by dx squared plus p of x equal to 0. And this equation represent a bar at x equals 0 and at x equal L, and in one dimension x, and defined by two boundary conditions. So this equation defined on this domain between x equals 0 and x equal L. This is the domain of the problem. And this is the 2 points are the boundary of the problem. These 2 points, this one and this one, are the boundary of the problem. We use the term gamma to denote the boundary, and we use the term omega to define the domain of the problem. And this is applied load here. In the previous lecture, lecture 1, we integrate twice. We direct integration. So what we did is actually not a solution of differential form. What we did is the analytical solution. Solution but direct integration. So when we integrate this, we needed two boundary conditions. So we have two boundary conditions here. Here is boundary condition 1 and here is boundary condition 2. Okay, to get the constant of the integration. But in this lecture, what we did is to start to think in different way. Then we said, actually, mathematically, this bar, actually, it is infinite bar. We are going to rebuild this bar again. It is infinite bar. But it is defined at this point by a certain boundary condition. Boundary condition number 1 at this point is defined by a certain boundary condition number 2. And this bar here, it is a part of infinite bar and defined by two boundary conditions. So by thinking now, I want to rebuild these boundary conditions again. How? The idea was very simple. Get two fictitious loads. So we placed the fictitious load here and we placed the fictitious load here. Why we placed the two fictitious load? Because we have two boundary conditions. I don't know the intensity of these loads. I don't know them. It's okay. Try. Provided that the effect of this source here and the effect of this source here will generate boundary condition 1 and boundary condition 2. In the same time, I will generate the effect of this one here and the effect of this one here. The superposition of these two here will generate the boundary condition 1. The superposition of these two here will generate boundary condition 2. Because of that, we call it superposition. Because of that, we call it superposition. So if we are able, by trials, by solution of equation, by any ways, to compute the intensity phi1 and the intensity phi2 to represent these two boundary conditions, that means direct, I will be able to represent the original problem using these two sources. So at the end of the day, my problem, instead of having my beam, we will return this beam to its actual mathematical view. So the actual mathematical view of this beam, it is infinite beam, but defined at these boundary conditions. It is like us. We are infinite. We are infinite. We are, as a human being, we are infinite. But actually, we are part of the infinity. Actually, we are confined inside our bodies, and our bodies are defined by our faces, our boundaries, our bodies. When we take the picture for us, we take the picture to identify yourself. This picture is you. So actually, it is your boundary. It is your interface to the world. So once you rebuild your face by using these two sources, maybe in our case, we need something like 100 sources or something like that to define our face and our characters. But once we have once we are able to use these two sources to define the boundary conditions here and the boundary condition here, so definitely the effect of this source inside the beam at this point plus the effect of the source at this point, the two superposition here is equal to the actual solution at this point. So it is u at this point, if I call it point y or something like this point y. So it takes the effect of this source and the effect of this source. Why we call it integral equation and it is summation? Actually, this summation practically it comes from Latin letter and the Latin letter actually is summation. And actually, if we stretch it out, this one will get it to the integral. Actually, this is the S of the integral, came from here. If you look at all the books in Greek or something like that, they don't use the integral sign, they use the summation sign, very big summation sign or something like this. Okay, so this is summation actually, because we make a summation for 2 points. Why we call it indirect integral equation is not direct integral equation? This is mainly because we are solving first to get the intensity phi to represent these two boundary conditions, to satisfy these two boundary conditions. Once we solve with this to get these two boundary conditions, we are able after that, after getting the phi, we are getting the solution of this problem, whether we need u, we need the strain, we need anything, we'll be able to get it as a summation of these 2 points. And here I'm going to say something a bit outside the lecture, but we have to be very careful to differentiate between the summation in the classical sense and the summation in the quantum sense. The summation in the classical sense, we have effect of the first source and the effect of the second source. But in the quantum sense, we have very different summation. The summation or the superposition in the quantum sense is very, very different. It is, once you have the observation, you will have either phi 1 or phi 2. Maybe later we'll be able to give some lecture about quantum mechanics or something like that. So it is very, very different in this sense. But now, until now, we have summation in the classical sense. So the effect at any point inside the beam, it is equal to the summation from the first source and the summation from the second source, and so on. Because of that, I like, instead of using the word the word indirect integral equation, I like to use the word superposition. You will find it in the literature under several names, something like indirect integral equation, indirect discrete integral equation. Maybe we are here discrete now because in one dimension, but maybe in higher dimension we will make it discrete, like the method of fundamental solution, source field superposition, method of moments, series of names under these names. But it is classically, it is 100% analytical. Until now, we didn't put any approximation. All of what we did is alternative way of analytical way. If you remember, in lecture 1, we are able to get explicit expression for u, function of x or something like that. But in this lecture, we are able to define u as u asterisk between point equal x, for example, at x minus xi1 times phi 1 plus u asterisk of x minus xi2 times phi 2. Okay, and phi is very well known values functions, and x is our variable, and xi1 and xi2 are equal. That means this expression is equivalent to this one. So it is a way to expand in series. So instead of having power series or Fourier series or Maclaurin series or something like that, we have ways to expand in series. It's like power series. We have Maclaurin series. We have Fourier series using sine and cosine. We have alternative way to expand in this way. Also, keep in your mind what we did here is phi 1 and phi 2 are discrete sources. Discrete sources. We could use dipoles, we could use quadrupoles and higher order poles. Okay, so we can expand in multipole in this way. Okay, this is the first notes we have about this method, and I hope you will be able to continue trials with this method.